Hello again. Thanks for joining us on Space Nuts, where we talk astronomy and space and science all at the same time. This is a Q&A episode. My name is Andrew Dunkley, your host. Great to have your company. Coming up, audience questions. We're going to answer a question from Martin about supermassive black holes. Ben has also got a question about black holes and gravitational waves. Andy, our favourite train driver, is on about Voyager 1, and Judd has some thought experiments for us. We'll check it all out on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And back to unravel, unpack, and solve all of that is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Very good to see you.
Good to see you too. I've still got my croaky voice. In fact, I've been so unwell, I'm still wearing the same clothes as I was last week.
Well, there you go. Funnily enough, so am I.
Yeah, well, what a coincidence. Shall we get down to business?
Why not?
All right.
There's nothing else to do, so yeah.
Now, we've got some text and audio questions. We'll go text first today, and forgive my rather unreliable voice as I work my way through this. Hi, Fred and Andrew. It's Martin here from Heswall on the Wirral in Merseyside. I posted a question before, and Fred mentioned that he knew Barnston, which is just a pleasant walk over the fields from here. I have a question about your favourite topic. Black hole. I thought it was going to be golf. Black holes. I'm interested specifically in the process of their formation, and more particularly in supermassive black holes. The mechanism for the creation of stellar mass black holes seems to be well understood, but I find it hard to believe that this can be the same way that supermassive black holes in the early universe were formed. I've read that the gravitational instability theory posits that black holes can be formed directly when a massive cloud of matter collapses under its own gravity. Why is it not possible that there can be two processes at work depending on the size? For me, part of the evidence in support of invoking gravitational instability is the lack of evidence for the existence of intermediate mass black holes. What are the arguments against this theory, as it doesn't seem to be that widely accepted? If black holes are created in two completely different ways, what effect would this have on their properties? For instance, charge, spin, etc. I really enjoy listening to the show. It helps me keep up to date with the world of science, space, and stuff. That's our slogan. Ha! Well done, Martin. That's our slogan. Yeah, look, that's a really good question. And we only talked in the last episode about the different theories about how black holes are formed and the possible discovery of primordial black holes. So if you haven't heard that episode, wind back, because it's worth listening to that story. But he brings up an interesting point. How can it be the same process for a supermassive black hole versus another one, a smaller one?
Yeah, so, I mean, Martin's hit on one of the key questions at the moment in astrophysics and cosmology, so he's right up to date there.
Yeah, he sure is.
Because this idea of the supermassive black holes in the early universe forming directly as a direct result of a cloud of gas collapsing without having to go through the mechanisms of forming a star and then the stars basically exploding to form a black hole. That's quite new. And that might be why, as Martin says, it's not yet sort of considered to be mainstream, but it is very much an up-and-coming idea and theory that answers the criticism that the conventional theory has, and that is, conventionally, scientists have assumed that supermassive black holes are created over long periods of time by the accretion of material. So we know how a stellar mass black hole is formed, exactly as Martin mentioned. We understand that a massive star explodes at the end of its life when the fuel balance runs out. The outer layers are shed off and a supernova remnant, and the center, basically the central core, collapses to be the black hole, which is a point with 0 dimensions, a point where density is infinite. So that the conventional method says you start off with lots of those in a galaxy, and they eventually accrete to form a bigger object, mixing with stuff that's sucked in on the accretion disk as well. That might include a few odd black holes dropping in to form eventually a supermassive black hole. But the problem has been, how do you manage to do that in less than a couple of 100 million years, which is, where the earliest supermassive black holes are after the Big Bang. We know about those because we measure them by using the James Webb Space Telescope. It's measured, I think, several objects within maybe 250 million years after the Big Bang. In other words, we're looking back almost 13.8 billion years, 13.6 or something like that. How did they form so quickly, if that's the mechanism? And that's why this alternative mechanism of direct collapse from an interstellar, not interstellar because there were no stars then, but from a primordial gas cloud might have occurred. And as I understand it, the idea of primordial black holes postulated, this is what we talked about last week, or in the last episode, postulated by Stephen Hawking, envisaged that there would be a very, very wide range of masses of black holes, ranging from things less than the mass of the sun, as we reported in the last episode, we think we've found one of those now, to supermassive black holes. I think that is all within the purview of Hawking's theory of primordial black holes. And so the question, maybe the fact that we're finding the supermassive black holes too early in the universe might to have been formed by stuff coming together might be a support for Hawking's theory that maybe some of these were actually formed immediately after the Big Bang.
Wow. Wouldn't that be interesting?
There was something about something that Martin mentioned about intermediate.
Yeah, he said, for me, part of the evidence in support of invoking gravitational instability is the lack of evidence for the existence of intermediate mass black holes. Although they're the ones we were talking about recently that we now have discovered, have we not?
Yes, but they're still
not many.
They still seem to be, much rarer than the supermassive black holes or the stellar mass black holes, which exist in profusion. Intermediate mass black holes have been quite hard to find.
Maybe they're just beaten up.
Yeah, I mean, what Martin says is right. That might point to the idea of gravitational instability, in other words, sort of primordial type black holes, as being the formation. That might point to that. And so I don't think there's an issue there. But yes, his final question, if black holes are created in two completely different ways, what effect would that have on their properties? For instance, charge, spin, etc. Now, in fact, the only properties of a black hole that you can observe are the charge and the spin, as well as the mass. And that's because of something that you and I might have mentioned before, Andrew, something called the no-hair theorem, which I'm very fond of, as you can guess. And the no-hair theorem basically says that there's virtually nothing of the black hole's characteristics that you can see from the outside. It's like suggesting a baldness of the black hole, the event horizon. It doesn't give much away. Charge and spin are, I think only the only two apart from mass. Now, I don't know the answer to that. Would there be any difference in those properties for two different methods of black hole formation? I think it's a really good question, and it's something that I probably should have a look at and see if I can find out.
Yeah, I thought I'd look up no-hair theorem to see what happened, and I didn't get an ad for a hair pill. It actually took me to the
to the no-hair theorem.
To the no-hair theorem about black holes. Yeah. So there you go. the internet actually worked.
Yes.
Nice change. Nice change. And a nice question, Martin. Thanks for sending that to us. Hopefully that helped you sort of few things out. But there's still a lot of theory around black holes yet to be proven. But we're chipping away at it. We are chipping away at it. Not me personally. I leave that to other people who are more astute. Thanks for sending it in. Our next question comes from our favourite train driver. His name is Andy.
Train driver here. Just a question for you on Voyager 1. I know that it's currently travelling about 38,000 miles per hour and it's very low on fuel, and the fuel is used for the thrusters to point its antennas back to Earth. And I know that space is not empty. There's particles and space dust. So because it's got such a long journey before it reaches anything significant, would the particles in space slow it enough to bring it to a halt? Because as far as I'm aware, it's got about 40,000 years before it reaches something significant. So is that a long enough time, would you say, to maybe not bring it to a halt, but to slow it significantly, that it really does increase that timescale? Sorry if that doesn't make much sense. Thanks for your podcast, guys. Really enjoy it. Speak to you soon. Bye.
Thank you, Andy. Hope all is well on your daily commute. Although you're the driver, so you just drag everyone else around. What a great job. Right, okay. Voyager 1, 38,000 miles an hour. Is there enough material to ultimately stop it? Because it's going to run into a few things here and there, possibly. But I would question the spread of the dust. When you get out into those interstellar places, the amount of material thins out significantly, doesn't it?
Yeah, very much so. There is still... there are still atoms there, or nuclei, probably subatomic particles, but it's not enough to significantly slow the spacecraft. It's you basically, to all intents and purposes, it's moving through a vacuum. I was thinking kilometers per second. Its current speed is 16.920 kilometers per second relative to the sun.
61,000 kilometres an hour, 17 kilometres a second-ish, 38,000 miles an hour. Yep. It's going. It's fast.
It is. The speed I like is in units of astronomical units per year, and that is 3.6, nearly 3.569. So 3 times a year, it covers the distance from the Earth to the sun. Yeah. So, that's 150 million kilometres.
Sure is. That's amazing, isn't it? And it's still going strong.
Yeah. So, and Andy's right. I think the fuel's low, but the fuel is just for the thrusters. It's just to keep the antenna pointed towards Earth.
So, and he said it might come across something in about 40,000 years. I thought when we talked about this last that it could just keep going. It might not run into anything.
Yeah, simply because it's not aimed at anything, and space is very empty. Even though there's 400 billion stars in the Milky Way or whatever, the Milky Way is very, very big indeed. And its distance is. I think the odds are that it will keep going forever. It might be captured by the gravity of another star. I think the notion of a collision is vanishingly small. I've just statistics just come into my head that I used to use a lot to give people the idea of just how big the galaxy is, and I'm sure you and I have discussed it too. If you imagine a diagram of our galaxy that was the size of the Earth, so 12,500 kilometres in diameter, that's your map of the galaxy, the size of the Earth. The separation from the Sun to the Earth on that scale is 2 millimetres. That tells you that the galaxy is very, very large compared with the size of the solar system.
That's just mind-boggling stuff. It really is. And the other thing, I suppose, like we talk about the Oort cloud, which is this thing around our Is it around our solar system or around a galaxy? I can't remember.
No, it's around the solar system.
Solar system,
it's a
yeah.
shadow.
Yeah. They reckon it's going to take 300 years for Voyager 1 to reach that.
That's right. That's right.
And
Still a long way off.
Which means it still hasn't really left our solar system in real terms.
I'm not even sure that it will be 300 years because the Oort cloud is about a light year away.
Well, actually, it says here the inner edge in 300 years, but it will take 30,000 years to pass through it.
That's more like it.
Yeah.
It's more like it.
So I should have finished reading the sentence, shouldn't I? Well, there was an unpredictable full stop in there, though. So but incredible.
I meant to say last time Andy came on, I meant to tell him that I'm a train driver too, but it's N scale, which he'll know what that is. Not some people might know. Actually, probably quite a lot of our listeners do. But I drive my trains in N scale, and I love it.
I should send Andy, if he sends me his email address, some video of our brand new regional trains in New South Wales.
Oh yeah,
that are being.
I'd like to see that.
Yeah,
too.
they're being fitted out in Dubbo, where I live, and they've been doing test runs on them. I've actually heard it in the wee small hours passing by because it's got a completely different sound, and I've actually reached a point now where I recognise the different trains by sound. How pathetic is that? But
it's
much quieter than the current train, which is the XPT, which is well past its use by date, but never let the New South Wales government, build a train because they will say, okay, it's got a 20-year life, so we'll replace it in 50, because that's what's happening. But these are very slick. These are Spanish trains that are being fitted out in Dubbo, and really, really lovely piece of kit, as Fred would say. So, and he sent me your email address, and I will send you a video of our new trains. It's weird watching them run around with nobody in them. It's just no passengers, nothing. Just all the lights are on. Nobody's home. Nobody's home.
Yeah, if you're on the metro in Sydney, there's not even a driver on board either.
Yeah, I know. I've been on the metro a couple of times. It's a slick system.
Oh, that's brilliant.
One of my boys lives in a suburb where they're just about to complete a metro line, so he's really happy about that because it'll get him to work, 3 times as fast. So he's thrilled because he got rid of his car. He doesn't use a car in Sydney. Doesn't see the need. Got to have one out here, though, in the country. Thanks, Andy. Lovely to hear from you. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Let's take a short break from Space Nuts to tell you about our sponsor, NordVPN. Now, I've talked about virtual private networks before and how they can protect you online, and no one does it better than Nord. Now, I've been using Nord for over 2 years and I have no complaints. I'm also using some of their other tools, including the brilliant password manager. NordVPN is great for streaming and won't slow you down. In fact, it does the opposite with no interruptions, no limits on bandwidth and no limits on speed. Right now, using the exclusive Space Nuts offer, you can receive 4 extra months for free on a nordvpn.com plan. NordVPN encrypts your internet connection, hides your IP address, and offers access to over 7,700 servers around the world. Plus, with features like Threat Protection Pro, MeshNet, ultra-fast speeds via Nord links, your digital life stays private and efficient. So don't miss out. Visit nordvpn.com/spacenuts and enter the code SpaceNuts to claim this deal. Remember, there's a 30-day money-back guarantee, so it's risk-free to try. Stay safe, stay private, and browse with confidence. That's nordvpn.com/spacenuts.
Roger, you're loud and clear here also.
Space Nuts.
Oh, boy. Okay, next question. I don't even know where we're up to. Where are we up to? We've spoken to Andy. All right. Question 3. Hi, Space Nuts. Ben Harding here from Kent, England. Having listened to your show for several years now, I know everything there is to know about black holes. Indeed, I'm ready to start building my own any day now, but wait. If I build two and they crash together, they will create gravitational waves, and I need to account for the ensuing distortion of the fabric of space-time, or my cats will be upset. So, are gravitational waves spherical or flat? I'm thinking they must be spherical, but then again, if they are created by two objects spiraling in together, the waves may be flat by some sort of conservation of angular momentum rule. I hope you can help me with my cats. They get a bit scratchy when they're upset. Thanks for the awesome show, Ben. Thank you, Ben. I'm just imagining your cats freaking out over gravitational waves. There's a comic strip in that, I reckon, somewhere. My brother would do a comic on that, I reckon. He's very artistic, is my brother. Okay, all right. So are gravitational waves from the cataclysmic collision of two black holes spherical?
So I think what Ben is referring to in his description is whether they're radiated. Gravitational waves are radiated in all directions, what we would call isotropic, or just in a plane, in the plane of the collision. And to the best of my understanding, the answer is that they're isotropic. They go off in all directions.
Right.
So space shudders just because of the gravitational interaction. It's not got any I do not believe it's got any preferred direction because of the direction of the collision. I think it is the same in all directions. There's another way of interpreting Ben's question, though, and that is how the oscillations of gravitational waves take place, and they're not the same as sound waves, which are compression waves where things push backwards and forwards. And they're not the same as light waves, which are transverse waves, where the electric field and magnetic field vary in a transverse manner. In other words, opposite to the direction of propagation, or right angles to the direction of propagation. There's something called quadrupole waves, which is a sort of combination of, not quite a combination of the two, but certainly a slightly unusual form of transverse wave. Quadrupole waves is what they are. But I don't think that's what he means. I think what Ben means is what I answered in the first place, that yes, they're isotropic rather than limited to a particular plane.
So they go out in all directions, unlike the gravitational wave that I detected on a plane. I don't know what that guy was eating, but I hope I don't have to experience that again.
I know about those things as well.
Pretty awful stuff, really.
Yep, they are.
I'm impressed that Ben says he knows everything there is to know about black holes.
Yeah.
Does that mean we've been doing our job?
That means he knows more than us, which is pretty easy to do, really.
Possible too, yeah.
Yes.
But we're learning more and more about them.
We are. That's because we listen to our listeners.
That's exactly right. But they've been the topic of, I think, since we started a decade ago, Fred. You reminded me earlier, it's been 10 years we've been doing this podcast. That's extraordinary. We should have had a party, but I think we just can't stay up that late anymore. But it's probably been the hottest topic on Space Nuts since day one, is black holes. Closely followed by dark matter, dark energy, and I don't know where you go from there, but it's been...
And life in space.
Yes, life. Yes, you are right. Those are the top 4 topics. So I expect next week our 4 questions will be on black holes, dark matter, dark energy, and life elsewhere.
Yeah, there's a good chance they will. That will be the standard.
Yep. Very good. Thank you, Ben. Lovely to hear from you. Hope all is well in Kent. Our final question comes from Judd.
G'day, Fred and Andrew. It's Judd from Brisbane. Been a big fan of the show for a long time. My wife and I were listening to a recent episode where one of the stories was about the spun out asteroid that's spinning at an incredibly fast rate. And, we found Andrew's thought experiments about how that would affect Earth if we were spinning at a similar rate And yeah, got my head spinning and came up with lots of other thought experiments. First, my question is, what is the current speed of the Earth's rotation? And yeah, does that speed affect the pull of gravity that we feel on Earth? Like, for instance, if I weigh 100 kilograms at spinning at this rate of speed, if the Earth stopped spinning tomorrow, would I weigh significantly more? Just wondering about that. And another question, would I weigh less at the equator than I would standing at the North or South Pole? Because the equator is spinning much more rapidly than the Earth is at the poles. So, just some thoughts to make your head spin and maybe give me some answers. Thank you.
Thank you, Judd. Thanks to you and your wife for being fans of the show for so long. Much appreciated. And we can make this quick. Yes. And we're finished for the... No. There's a lot more to it than that. But I think he pretty well nailed a few of the thoughts that he's had in terms of what the answers are. What is the current speed of Earth's rotation? If you listen to the Monty Python song from The Life of Brian, or was it one of the others? Yeah, they were wrong, weren't they, with their assessment of the speed of the rotation of the planet?
I can't remember. I do remember, I don't know what the speed is, but I'll get to that in a second. I can't remember what the song says, but I do remember listening to that song a long time ago and thinking, yeah, pretty well most of the astronomical statistics in it are correct. Or they were when it was written back in the day. But Judd is right. The speed of rotation at the Earth on the equator, which is where your linear speed is maximum, is 1,600 kilometers an hour. So that's significant. It's about half a kilometer per second, roughly. And that's why you tend to build space launch sites at the equator, because you've got that additional 0.5 kilometers per second that's quite significant when you're trying to get up to 8 kilometers per second to get into orbit. So you're kind of a 16th of the way there already, just by putting your launch site on the equator and, of course, launching towards the east, which is the direction that we're rotating in. At middle latitudes, it reduces. At our latitude here in New South Wales, it's about 1,400 kilometres per hour. At Judd's latitude in Brisbane, it's a little bit less, not that much less though. But so what's the effect on your weight? That's the interesting thing.
Yeah.
And there are two parts to this. One is kind of what we've just alluded to, the fact that you are rotating 1,600 kilometres an hour, roughly 1,000 miles an hour. It basically, there's a centrifugal force that means that you are slightly lighter. Your mass doesn't change, of course, but your weight does because of that centrifugal force. But there is another effect that acts with that too, and that's because the Earth isn't spherical. It's slightly bulging in the centre. It's what we call an oblate spheroid. And at the equator, you're about 20 kilometres further away from the Earth's centre of gravity than you are at the poles. And so that too reduces the gravitational pull that you feel. So those two things together, the equatorial bulge of the Earth and the centrifugal force of the Earth's rotation, they basically combine to give you a figure that's a bit less than 1% of your weight changes if you're at the equator compared with the poles.
That'd be a lot for some people, maybe.
Yes, yeah. I mean, it means that if you do weigh 100 kilograms then at the equator, then you're only going to be 99 at the pole.
Yeah.
No, I've got it the
other way around.
If you're 100 kilograms at the pole, you're only going to be 99 at the equator.
I knew what you meant.
Yeah.
Yeah, it's fascinating, really. And yeah, that was one of his questions. Weight at the equator versus the poles. What would happen if Earth stopped spinning? Like, I think we'd all be doomed, for starters. That'd be the end of that. But
we'd all be projected eastwards at 1,600 kilometres an hour if you're on the equator.
Yeah. Yeah, that'd be pretty messy.
But if the Earth stopped spinning, you'd only have that equatorial bulge component that's reducing your weight, the fact that you're a little bit further away from the centre, and that's almost negligible on its own.
Yeah, fair enough. That was easy. And I found that Monty Python song, it was from The Meaning of Life, not from The Life of Brian.
That's right.
And it's called the Galaxy Song. And the first verse says, just remember that you're standing on a planet that's evolving and revolving at 900 miles an hour.
Which is, yeah, all right. So
they're a bit slow.
100 miles an hour slow.
Yeah,
that's right.
But it rhymes.
That's it. 1,000 would have rhymed.
It would have worked. Yeah.
Yeah.
Oh, well, maybe they needed 2 words rather than, no, it would have still been 2 words.
Or, Andrew, maybe the Earth has speeded up since they recorded the song.
That's possible. It's slowing down, though, isn't it?
Yes. Yeah.
Well, eventually their song will be right.
Yes, it will. That's right.
Oh, gosh. All right. Thank you so much, Judd. Lovely to hear from you. Hope all is well in Brisbane. Sorry about your football team. Not. And I think that brings us to the end. If you have questions for us, we would love to hear from you. You can go to our website, spacenuts.io, and click on the AMA link at the top of the page where you can ask me anything, or ask me and I'll give it to Fred to figure out. So send us text and audio questions. Don't forget to tell us who you are and where you're from. And a little request, if you will, when you next listen or are listening to us right now, please leave a review on whatever podcast platform you use, because reviews are very handy. It sort of moves us up some laddery ranking thing, which is very good for us, apparently. I don't understand how this works. It's all to do with gravity. And thank you, Fred, once again for helping us out today. I think you did all the work, actually.
Nice to help, Andrew. Always good to talk, and we'll catch up again.
We will. Professor Fred Watson, astronomer at large. And thanks to Hugh in the studio. Although he couldn't be with us today, he had a thought, and it was experimental, and he's going to go and investigate that right now and see if it's real. I don't know what that means. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.